Hello, am I audible? So, about yesterday, I was not attentive and I recorded the whole thing with no sound. I'm so sorry for that. So, I'm redoing it again. So, please bear with me, and I'm sorry once again for not keeping mind about the audio. So, I will try to explain all of the topics all over again. Yesterday, we went over quite a topic, huge number of topic, but sadly no sound was recorded. So I'll go over again. No problem. I'll go over again. So before we start, I yesterday went over our day one as a flashback to the day one because it has been a very long day. The first session was on 7th February and the next one was on 21. So it was a huge gap. Some concept might get be vanished from our mind. That is very common and normal. So let's begin as the sound is okay now, and let me see if the alignment is okay or not. The alignment is also okay. So to the begin with, we started with a model which was our supervised model, which was the very common and the basic model, which was linear regression. We started with that as we had given input data set and output, all of them were given, but we wanted to get a more feasible value. So we added biasing value and more things to that so that we can get the optimized output. So we can conclude a short image of linear regression. I'm not going to dive detail in case of linear regression because that is not our topic for today. So moving on to the second point, which was how we can represent a system of equation and how many data set and how we can represent it in uh, vectors or matrices in a simplified approach. If you want to see that, let me show you. Wait a minute if you want to see that. So our initial data set was this, and our model equation was this y equal to wb. So our initial equation was y equal to um, wx by b, where b was our biasing value and w was somewhat of a weight here. So this was our basic model, and we expanded this model into for a larger data set scale. So it was like this. So Mm, Zoom it a bit. So we were initially working with this, but it is very tough to do calculation with this. Then we simplified the system by converting it to into a vector and matrices previously. If you are interested to know in details, you can see this blog of mine. I will share the details. So that was for the second thing, for the second point. Now for the third point, which was our system of sentences, where we learned about how words can give us an idea of a system, or how a system is defined by its informativeness, how a system is informative based on its uh, characteristics or attribute. And from that we advanced our concept by knowing where how we can do a analysis or come to a conclusion how the system is behaving. If is it behaving like a singular, or is it behaving like a non-singular? So we figure out that. Then, and after doing kind of rough analysis, we figure out that we can do a short analysis, no, shortcut of figure outing whether a system is singular or non-singular by figure outing its determinant. But I am assuming that most of you do not know what is the basic operation of matrices and how we can do it. So I am going to show you that. That is our agenda for today. So our matrix is typically something like a series of number that are in column and rows. So let's say I have a matrix A. We are naming the matrix A, and we have some array of numbers. I'm checking if I'm audible or not. Now let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have to give this big bracket similar to third bracket. It's not straight because I'm doing it by hand. So this is a typical matrix, and its row is, if you feel confusion which one is a row and which one is a column, this vertical one is column and the horizontal one is um, row. So here this one, 2, 3 is in row, and this one is a column. So if we want to know the shape or order of this matrix, this would be a 3 by 3 because there are 3 rows and 3 columns. Here the first three is indicating the row, and the second one is indicating the column. So these two all overall representing the order of a matrix. So let's try with another example uh, to understand the order of matrix. So let's say we have B. Can you tell me from previous understanding, just I said, what would be the order of this matrix? Please write it down in the comment section if you can. No worries, I will tell you the answer. Day. So, as there is no feedback, I am just revealing the answer. The order of this matrix would be As we can see, there are, I'm breaking it in simple and it might take a long explanation, but there is two rows. So we will write 2 here, then multiplication sign. Then we can see that if we want to figure out how many columns are here, that would be 1, 2, 3. So the order of this matrix would be 2 by 3. So this is some simple properties of matrices. Now I want to show you the types of matrices. So to begin with, mm, sorry for my bad handwriting. I'm not used to writing on graphics tablet. So the very first one would be row matrix. We will slowly dive into the complex one. So you can already guess how this matrix would look like because it is a row matrix and it would comprise of a row. So it would look like, the example would look like R1, R2. The values of R4, R1 can be anything. I'm just writing the entries in general arbitrary form. So this is a row matrix where we can also figure out its order. Here we have one row and 4 columns. So the order here is 1 into 4. Moving on to the second one, column matrix. You can already guess this one. The very first types are very easy to guess and easy to understand. So you can already guess whenever I'm mentioning their name. So it would consist of only columns. So this would be like this: C1, C2, C3, C4. And if you want to know what would be the order of this one would be 4 into 1, the opposite, just the reverse. Now moving on to the third type, which would be a interesting one, and you can also guess this one as I'm saying. And now I'm going to say the name. The third type that we are going to know is zero matrix. So zero matrix is something that we can already guess the values can be anything, but it cannot be anything but zero. It must be zero. All of the entities must be zero. So zero, 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 zero. And if you want to know a good sorry, a good definition of a square, a good definition of a zero matrix, then it would be like, uh, a zero matrix is a square matrix where all of its entities are zero. As you can see, there is no other values other than zero here. So for that reason, it is named zero matrix. And why am I saying it is a square matrix? Because you can see by the nature of a square, all of its sides are similar in length. So here we can see that the number of rows and the number of columns here are same, which is 3 by 3, which is denoting that it is a square in nature because of its equal number of rows and columns. So that's why I'm saying that it is a zero matrix is a square matrix where we can say that all of the entities are zero. And following this definition, most of the other types are similar. The definition is similar in nature. They follow this one. So moving on to the fourth type, that would be a singleton matrix. So a singleton matrix would be like a single value, like one. This is the singleton matrix. B. Um, uh, this two matrices A and B are both represented in singleton matrix. So now moving on to the fifth one, I'm using the same board as yesterday, so the previous writings are from yesterday. 5, that would be our square matrix. As I said before, what is a square matrix, but I'm going to say it again why it is a square, because of having equal number of rows and columns. So this one is a 3 by 3 square matrix, this one is a 2 by 2 square matrix, not because of the values 2, because of the number of columns and row here is 2, not because of the scalar value 2. Now moving on to the uh, moving to the sixth type, which would be diagonal matrix. So you must get an idea from the name diagonal. The value must be in the diagonal. So that's why this matrix is named as diagonal matrix. So you can already guess, and from simple understanding, you can visualize this matrix. They are very easy to guess and visualize. So anyone can understand. So let it be 1, 2, 3, 0, 0, 0, 0, 0, 0. So the condition of a matrix to be a diagonal matrix is that only the values in the diagonal, the primary diagonal here, if you do not know what is the primary diagonal, this one here, this little straight line is diagonally, the diagonally straight line here is the primary diagonal, and the in the flip side here, the 0 to 0 is the secondary diagonal, or it has another name I cannot recall at this moment. So in case, in both scenario, if I am working with this diagonal or the another diagonal, the other entries must be 0, otherwise we cannot say this is a diagonal matrix. So if any of the quantities or entries here, if any of the 0 is 2 or 3 or something, anything of a number, then it cannot be a diagonal matrix. Now moving on towards lucky 7, that would be scalar matrix, and that is also similar, but there is a condition which makes them apart from diagonal matrix and scalar matrix. So what is the difference that makes them apart? So if you want to declare a matrix with a scalar, its uh, value must be same in the primary diagonal. So what I'm saying is that in the primary diagonal here, for let's say we have an array 0, not 0, If we give 0 here, it will be our 0 matrix to begin with. So now let's say lucky 7, 7, 7, 0, 0, 0. So why it is a scalar matrix? Because we are putting all the same values in the primary diagonal here. So one of the condition must be that all the entries in the primary diagonal must be same. Must be sorry, 7 must be same. Sorry, same, and it cannot be 0. It cannot be 0. Highly, it cannot be 0. So if it becomes 0, then it uh, goes back to the 0 matrix. So as I said, there is a difference in diagonal matrix and scalar matrix. That's why they are different. Otherwise, they would be the same thing. The only difference between them is in case of the entries, value of their entries. So you can see that in case of the primary diagonal of the diagonal matrix, there are three different values, 1, 2, 3. And in case of a scalar, as I said, the condition that all the entries must be the same value. If it is -7, all of them must be -7. It cannot be like one of them is -1, -1 again, then 1. You cannot do that. They must be similar in signs and symbol. So you cannot do that. And moving on to the another one, which is a fun one. I'm just going to show you from the yesterday. Or should I do it again? Let me show you from the yesterday slide because I am taking much time writing it down and drawing. So our very eighth one would be identity matrix. So you can say that the scalar, the diagonal, they are pretty much similar just because the values are in the primary diagonal, but their values in the primary diagonal is making them separate. So how can we say this is an identity matrix? And this is a very crucial matrix in the linear algebra world because it helps us to figure out any in inverse of a matrix and many complex calculation, so that we can deduct a value easily, so that we can reduce the computational time. But if we have many rows and arrows, uh, then it would be difficult for a calculator to do, but it varies for a device to device their computational power. So that is another thing for another day. Now, what makes it a identity matrix and why is it so important? So it is an identity matrix because simply because in the primary diagonal all of the values are 1. So, and why it is so crucial, as all of the values here is 1. So if I multiply something, let's say a certain matrix with this one or something, to check the natures of some theorems, and if you want to figure out certain values or cross check, we can use this identity matrix to verify for verification purpose. And another thing, same as before, the values cannot be 0 in the primary diagonal, otherwise it will go back to 0 matrix. So we must avoid that. And one important finding is that all identity matrices are scalar matrices, but all scalar matrices are not identity matrices because here all of the, if we have 7 here like previously, we cannot verify something because it is kind of multiplicative of 7 and 1. So it is 7 times of something. in nature if we compare to the identity matrix. So if we were to figure out a into a inverse in case of this calculation, or if we multiply it by an identity, then we would not get, if we want to write here, mm, let's if you want to do in simple, this is how we would do a into I here. The I is identity matrix. So if we multiply this value, you will ultimately get the value a. Simple, because all of the values are zero here. We are only multiplying with a. So I'm not sure whether I write it correct or not. Please do let me know if I'm wrong or not. I'm not sure about this, so I'm reviewing it. So basically, we cannot do the verification purpose, but it is very crucial for identity matrix to be one. So moving on to the ninth type, that would be triangular matrix, because you can see that it is forming a triangle above the primary diagonal here, so its name is kind of triangular matrices. So there are two types of triangular matrices, upper triangular and lower triangular. So how can we decide the upper and lower thing? So here the primary diagonal is acting as our axis. So sorry, I just was checking the comment section. So wait a minute. Sorry, I'm back. So as I was telling about how we can come to a conclusion how the matrix is upper and lower. So the primary diagonal is acting like our axis here. So if the values are above the primary diagonal here, so it would be a upper triangular. My triangle is not pretty here. Sorry for that. I'm not a good artist here, but I give a second try, and this one in the lower triangular matrix, it is seems like a sandwich or triangle in nature. So I'm very proud of that. So as you can see, the primary diagonal is acting as an axis here, and the values are below it. So we are saying that this is a lower triangular matrix. So this would be all for the triangular matrix. Now moving on to the very last one, which is symmetric matrix. So why am I saying is a symmetric matrix? Because the values, if you give a attention here, let me remove this. I explained, that's why it was very rough in nature. So you can see that the values in the row and the column are same, and if we replace them, the row in the column and the column in the row, it looks weird, but remove it. So if we switch their position, it is not doing anything. It is um, replicating the same matrix, so it is not bringing new to the table, so it is maintaining its symmetric nature. So if we wanted to see if we switch, let's say this one is 2 3, that's the prime. Then if we switch, then this 2 would be here and this 2 would go here, and this 3 would go here and this 3 would come here. So if we remove this prime sign here, then is basically the same thing all over again. So I'm remove it for the understanding. So it is basically indicating the same matrix. So it is kind of a cool things maintaining symmetry. So if we figure out a transpose of A, which is switching the rows and the columns, so the algorithm of transpose word is that we are switching the places of the rows and the columns. So it is like A prime for that reason. And if you want to have a clear idea, you can see here just we are switching the rows and the columns, and that's all. You cannot even see the difference here because they are returning their symmetric in nature. So now that we are overall done with 30 minutes of the session, I'm still talking about the types. Let's move on to the basic operation. That would be fast very addition. So let me go to a clean space. Uh, Here I am. So we are moving on to the second topic. And if we have enough time, and if you are here for a long time, then I would show you a bonus activity as an apology gift, because yesterday we couldn't enjoy the session as there was no sound. So I will try to do that if we have time. So basic operational matrices. So to begin with, if we have two matrix, let's say, um, I'm just showing you the algorithm, but I'm not going to show you an example unless it is required. I'm just going to show the example of the addition, because if you understand the addition of the matrix, you will basically understand the subtraction of it. But if I don't show you the approach of multiplication, you won't understand, because the multiplication in case of matrix is bit different and special. So I'll show you all of the algorithm there, but I will not go into the details because I have more content to show you. So sorry in advance. So to begin with the addition, let's say we have a matrix A, and these values are A1, A2. It looks like 0, so let's assume it's not a 0, it's a 1. So now we have a matrix. Let me zoom more. And another matrix B. Sorry for my bad handwriting. My handwriting is very pretty if you have seen my handwriting in IRL. So sorry for my bad digital handwriting. I'm not used to writing on a tablet. So if I wanted to add this in simple addition, we would like, if we had two decimal numbers like 2, 3, the result would be like 5. Easy as that, but we cannot do some things if we are doing handling of a matrix. So if you are dealing with a matrix, the addition must we must be very mindful of the position of the rows and the column. And one thing that you must keep in mind, if you want to do an addition or subtraction or anything with a matrix, their order must be same. So very important thing that the matrix that we would be dealing for the basic apportion one, they must be in same order. The matrices that we would be must be same order, which is a must. Otherwise, you are doing a wrong addition, and you will get zero in exam if you encounter a matrix addition. So now that I have a 2 by 2 and another 2 by 2, they are retaining the first condition, that is to be same order. So I'm now going to add the first row of the first matrix, that is A, and this one. So how would I add these two? So if I want to add these two very numbers, so I have to be very careful. I must not add this row with this one. We have to be systematically. So we must add the very first entity here and this one. We will add these two, not how to show you. Hmm, will not write something like a plus a2 plus b1 plus b3. We won't write this. This is wrong. This is how we won't add. So the correct addition would be like a1 plus b1, then again a2 plus b2, and there is a gap here. I'm not writing in the same line. There is a gap between them so that you don't get confused. Again a3 plus b3, a4 plus b4. So now I'm going to remove this straight line, but for the sake of understanding, I'm just, should I, no. So this would be our addition or the sum of the product. So we must be careful. We must not write this all together in a straight line. There is a partition. We won't give a addition here. We are not adding all of them. We are just adding the entry in sorry, entries in the first. We are just adding the first value in the column or row. So we must be mindful of that. And similarly, in case if we are dealing with subtraction, I'm just going to show you in the very same example. Because we don't have much time, we just simply minus here. We'll just simply minus here. So that would be like that. Now, so sorry. Now that we know the addition and the subtraction, the basic three, sorry, but the basic two operation, now we were going to know about the special one, which would be the multiplication. So, um, let me see whether I can show you the yesterday's one. Hmm, I think I'm going to explain it from the yesterday's snippet because I want to save time. Sorry again for my bad handwriting. Again, all over again. So sorry. So let me remove some things so that you don't get confused. Mm, so if we were asked to figure out the value up to matrix here, which is A and B, what would be the value of A, B here? So as we know until now, the addition and subtraction here. So we do not know how we can come to the conclusion of how we can figure out A into B. And if we can recall our very first condition of in doing any basic operation for a matrix, their order must be same. Other than that, we cannot do that. But in case of matrix, the condition is little bit different. The condition is that the number of column of the first matrix must be equal to the number of rows in the second matrix. So if we were asked to do a multiplication of this one, we can see that both of them are 2 by 2. So the condition is satisfying. But in case of this one, let's see whether they satisfy the condition or not. So our A matrix is the first matrix. This is our first matrix, and the B matrix is our second matrix. So the condition was that the number of columns here, the number of column is 3, 1, 2, 3. And in case of the B, the number of row is 3. So we can perform this calculation, and their resulting output would be like, we can also figure out that from their order. So if we were given, if we write their order, so uh, if we write their order 2 by 2, 2 by 2, not this one. So for A, the order was uh, 2 into 3, and in case of B, it was 3 into 2. So their resulting output or the resulting product matrix would be 2 by 2. And we can conclude that here the column is same and the row is also same. Sorry, it is not multiplication. We're not multiplying that, just showing that they are same, so we can perform the multiplication. So now that we understood the condition, now let's see how we can multiply them. So if we want to multiply matrix here I have written the generalized form so that you can understand. Here we can see that we have a matrix, uh, example of a 2 by 2 multiplication of both 2 by 2 order. Here A is given, B is given, the values are A, B, C, D, I, J, K, L. This is L. So if I want to multiply this row, uh, let me zoom. If I wanted to multiply this row AB, what would I do? So you would select this one, keep one of your hand here, and we would simply multiply this row with this column. So and the value would be like A into, let me write it here, the snippet. So the value would be like A into I plus B into K, like that. But where would we put this value, right? We have done the multiplication. Now where should we put the value? If we can remember few moments ago that the resulting output would be like 2 by 2. So we would put this value here. As we are dealing the first row and the first column, and their common intersecting point is here. If you map this A and B here, you will see that B and I are mapping over here. For easy understanding, the value would be, the resulting output would be here. So same goes for every single operation here. yeah, for its position. So if I'm multiplying this a and b with j and l, the value would be in the j position because their common position b and j is here. So similar for in case if we want to multiply cd, we will basically perform this row first, ij, ik, then we would perform this jl. So then we will have an resulting matrix like this. So we'll add this value and get a certain value. If we are given values, then their resulting output would be like this. So now that we know that how we can do the multiplication now let's go over the how what topics that I have covered until now. The topics that I have covered until now are recap of the day one, types of the matrix, which are 10 types, and the basic operation. Now should I let me see whether we have time. We have 10 minutes if we want to stay for 1 hour. So let's do one thing. Let me explain one short topic in short, then we will go over to our bonus activity. Let me fix the bonus activity. Wait. If you want to like go over the topics that I'm talking about, and if you are not understanding or feel like I need a more elaborate explanation, you can simply refer to my blog where I write, where I have elaborated in detail. If you want to know in easy simpler words, then you can do that. And let's see whether we are okay. So the bonus activity is okay now. Mm, okay, it's now okay now. So as I said, I wanted to talk about a certain small topic before we go there. So let me go to us mm, here. So let's say I have a system, mm, 5 by a, 5 by a plus b equal to 17, and 4a minus 3b equal to 6. And let's assume the this is the system 1, and throw some algorithm or so some raw operation. If we convert this into a matrix, um, let's write something appropriate here. Let's just throw some process. We get to our solve system, which is the values of a and b here. So what would this sum process define? So what are that processes? So how can we simplify the system one and achieve this solve system? There is an approach, and that approach is that we want to eliminate one of the variables here. So let's say I want to eliminate a because it is the first letter in our alphabets. Other than that, no issues with A. So now that I want to eliminate this A, how would I do that? So if I want to eliminate this A, I would simply give focus to its coefficient here and here also, because we would divide this coefficient by 4 to every single quantity here and make the A single. So now that we want to eliminate this A, this is our agenda. We want to eliminate A and keep B into the plan. So we would divide 5 by A plus B by 5, 17 by 5. I'm writing in this term so that you can understand, because some of you might divide both of the equation by 5, but we won't do that. If we do that, the calculation would result in something different, so we must be mindful of that. We will simply separately divide the coefficient so that there is no confusion. So 6 by 4. So now that we can see that simply the coefficient of the a's are vanishing, and there's now single. Now what we are going to do, we have done our step 1. Let's say this one was our step 1. So what we would do in case of our step 2, so we want to subtract the equation 1 from the 2. So if we want to subtract the equation 1 from the 2, the answer would be like the a would go away. A minus 0.75 b equal to 1.5, a plus 0.2 b equal to 3.4, and the a's will go away, and we would end up with 0.95 negative, because we are subtracting here. The answer would be like this, and ultimately the value of b would be something, the minus would also go away, because same symbol on left hand side and right hand side. This is a normal thing. So this result would something be like 2. So we can come to a conclusion by eliminating a, the value of 2 of the solved system. One of the values of the solved system is 2. Now if we want to figure out the values of a, we can simply put it back. Sorry, I do not know if the alignment issue happened again. So we are subtracting the equation 1 and the 2 here. So we ultimately get the value of b, one of the solved system answer, which is b equal to 2. So we can simply put any of them in this equation. We can also put the value of uh, 2 here, to our beginning system, the beginning. So we can put the value and get a certain value of a, and that would be all. If we want to figure out how we can go to a solved system from this given system, this was kind of manipulation, manipulating the system by eliminating the a and solving the value for a and b, and it has a unique value a and b. So as we have a solved system with a and b with a certain value, we can say that the system is singular. But in case we are dealing with a, if say let's say one of the coefficient is not here, then it is making our approach is much easier, because one of the a is already eliminated. We can simply deduct the value of b here, and that would be like -2, and simply put the value in the first equation here, and that would be all. And but our system is not non-singular here. That would become, the system would become singular. Now that you know the approach of solving a linear linear equation, whether it's singular or non-singular, I want to tell you that you are basically applying matrix row reduction. So if we have a matrix, let's say previously we had the system here was 4. At a moment, so here was 4a. So let's write it here. The original system's matrix would be like, if you want to represent that in a matrix form, that would be like 5, 1, 4, -3. And performing some manipulation, we like eliminating we got to uh, intermediate system. That was like 0 point. This was our system, intermediate system. And now we move to our another system. We are just saying the flow of the system, how we are going from original system to an intermediate system to a solved system. So the solved system was like let's say the value of a would be like 3 and 2, 3 and 2 and 0 0. Let's assume that for sake of understanding. So if we divide the equation to further, we can also get to our one moment. I'm just little bit confused. No, the solve system is not this. Because ultimately, if we visualize this one, you will understand why I made this mistake. So here we came to a conclusion that the value of 3 2 here. So it is indicating that we can also convert this small system into a equation. So if I want to convert this into a equation, that would be like 1a plus 0b equal to 3, 0a plus 1b equal to 2. So if I want to represent this into a solved system, I should not write like previously I wrote. So I should write something like 1, 0 with the coefficient. We must create the matrix here with their coefficient. So I made a mistake earlier. So this would be our solved system. So We can also solve this system in matrix, but a few moments ago solved it with linear equation. So we can see that we are going from original system to an intermediate system through some manipulation, which was um, eliminating a by is dividing by its coefficient, then subtracting the equation 1 from 2, then we can further simplify this whole thing can be also operated by from the matrix form. We can simply perform some matrix row operation, which are basically these things in graph. We can perform them and reach to this conclusion. And if you know that we are basically performing um, this if you want to know another form of this in matrix world, that would be like row echelon form. And the solve system is kind of reduced version of that, because we are further simplifying that to complete one. And this would look like our flow of the system. And one more thing that I want to share is that if we are performing certain row operation, it is retaining its value of um, retaining its value of and preserves the property of singularity. So if we have a matrix, let's say if we switch the rows, but initially if we determined the determinant here, so it is like 15, 15 minus 8, that would result in 7. So if we change the rows, so if we'll be like let it be b. So if we switch the rows, you'll see something interesting. If we now determine the determinant, we can see that 8 minus 15, the value is just simply the opposite in sign. So it is retaining the property of singularity. So even if we switch the position of a row in a matrix, it is retaining its singularity nature. And similarly, if we add the second row with the first one, then determine the singularity, it also retain its singularity form. So let me show you that. Let's say I added the first one, that would result in like 7 and 3 by 2. Yes, 7 by 7. Then it would be like the determinant 14 minus 21. It also result in minus 7. Yes, minus 7. So it is retaining its singularity property. But if we do something like if we do I missed out important thing, that if we multiply a matrix with a certain constant or a scalar value, it would get multiplied to all of its entities. So let's say I have a scalar value or a constant value of 2, and if I multiply that 2 here with the matrix 1 1 4 8, all of its value would get multiplied here. So our resulting output would be like 2 2 8 16. And if we want to Now, if I want to show another thing of the singularity, I must multiply with the initial one. So let's say I am multiplying the two here. So our initial matrix was 5, 4, 5. Sorry, 4, 5, 3, 2. And if we multiply it by a scalar value 2, then the resulting output would be like 8, 10, 6, 4. What I'm trying to show you something interesting. So now that all of the entries are multiplied by 2, so what would happen in case if we want to figure out the determinant here? So if I want to figure out the determinant here, so I'm determining the determinant here, the 32 minus 60, the answer would be like uh, 0. The moment I'm just fumble now. Wait a moment. I just got to know I'm not showing the right uh, tab. I do not know how which rows that I have shown until now, which topics that I've shown. Let me go to the live again. The net is. I cannot go back and see it, but I think I am not showing the right screen for a long time. Hmm, let me go over again shortly. So I was showing you how we can solve a system or reach a system, solve system through some processes. So the first step would be like eliminating a by dividing by its coefficient. So if you divide the first equation 5 a by 5, b by 5, then a would be like 4a by 4, then the resulting equation would be like this, then we will solve, then we'll get a value b, then simply if we put the value of b in here or this equation, we would simply get the result and reach to a solved system. And if we want to know how we can know the row echelon from, so we solving the system or the matrix from basic operation. Sorry. So if we want to reach from original system to the intermediate system, we are performing some basic row operation like this. If we are originally solving the system like this in matrix form, we can do the basic swapping of rows and addition, then we can reach to this system, intermediate system, as like before. And this form would be like row echelon form. Then we can further simplify to this identity matrix form, that would be like reduce from reduce row echelon form. And this was like step one and step the flow of solved system from original system. So now that we know how to approach a system which is non-singular. In case of if the system is not non-singular, it is making the process of solving system easy. Let's say we don't have I'm just repeating. Let's say we don't have here, so the system becomes singular in nature. So we can simply figure out the value of b here, and put the value of b here and figure out the a. So we would do that easy. So basically solving a linear system, whether it is single or non-single, the approach is same. We have to eliminate one of the variables associated here, then we can do some manipulation like subtracting and division of them, then we can reach to our solve system. Now I want to show you the bonus activity here, but before that I want to show the singularity, that the row operation are maintaining the singularity property. Again, I'm going that over again because I was not showing the right screen. So if we look at here, if we take a matrix like 3 2 4 5 and determine the determinant of here, the value is 7, and if we switch the rows here, and we would simply get the same thing but in opposite in nature, sorry, opposite in sign. So it is retaining the singularity property. And if we simply add the second row with the first one and again determine the determinant, then we'd see that we are basically getting the same thing. So it is retaining the singularity property. And if we want to show another scenario where it is retaining its singularity, so we had the initial matrix A 4 by 4 5 3 2, and if we multiply this by 2 we would get like 8 10 6 4. And if we figure out the value here, we would get something like minus 28. That would be like something 7 times, it's like 7 times into 4. So it's into 4. It is like similar, just different. Did I do the multiplication right? Multiplication and subtraction right? I think so. So it is maintaining its singularity property regardless if I am taking a scalar and multiplying that. So it is basically so. Now that we are done with the concept, let's go to our bonus activity. So the bonus activity here would be like seeing hands-on of the code here, so that we can in our very next day we can do some of the solve of the systems like this in so that we can wait solve these equations in the code, so that we can do that. Now that we are here, so it is a one kind of Jupyter notebook or a kind of notebook, or but I'm showing you a cola file here which is similar in Jupyter format, Jupyter notebook format. If you are familiar, you will understand that we have separate columns, separate cell here, and we can simply run them and see an output. So it doesn't affect if this is in, if I write this here I would simply get the same thing, and if I don't write that, let's see we whether we get the output of the value test here. It is taking a bit time. So now let's see. He's saying that hello world it works. But we must run this at first, but otherwise we won't get a value. So the very basic library that everyone works if you want to dive into machine learning or data science, that would be uh, NumPy. So we are going to see the just basic of the NumPy today, introductory part. So NumPy is mainly a package or a library of a Python that you can help to design an array and do the array operation. So how you can do the calculation. But if you want to import an array in your IDE or a Jupyter notebook or Colab file, you have to write this in the cell, which is import numpy as np. Here we are simply declaring a short form here as np, so that when we are writing here, you can see that another argument here, np.array. So we had to write numpy every time other than otherwise. So we are writing np in short, so that we can um, keep track of what libraries that we are using. And if you do not know how we can assign a variable here, so here the test is a variable and we are assigning a string value. A string value is something that has quotation, and it is alphanumeric or anything. You can, then it can be a digit or anything, but it must be in quotation to be a string. So now that we know how to import numpy library, we must run this at first. Other than that, we won't get a value here. So if I want to see, wow, the one dimensional array here, because we are dealing with one dimensional here, so it is a 1D array. Let's see how our 1D array would look like. It is looking like 10 and 12, because in the list that we have passed here is 10 and 12. And how do you know it is a list? Because here is the comma here, and in case if you are representing array here, there would be no comma or any other thing. There would be a gap here. And how you can create a numpy array, from the step 1, you can see that we assigned a list or passed a list as an argument in the function array of numpy library. So we are basically declaring that I have an variable one dimensional array and passing a list. Please convert that list into an array. So this is doing the baby steps here. We can declare an array using a numpy in multiple ways. So here I have shown you three kinds of. Here you can see that we can, the first one is simply the previous one, and in case of the second one, we can see that we are a range a range. Here is, we are declaring that our default integer values start with 0 and it must end in minus 1. So we are declaring a range. So it would give us a certain array. So if I write here something like 19, we would get up to 18. So starting with 0, we would get 18, and n minus 1. We will basically get n minus 1. If I write 7, we are getting n minus 1. So it is like the similar, it is looking similar to the predictable, but it's not the predictable. So now that we have done the level 1, level 2, let's move to the level 3 of how we can declare an array. So if I want to specify a certain starting point of my array and increment a certain value and show that my array must end by a certain value, which is 20, how would that array look like? So something like this. So you can see the increment value from each value or entities here is 3. Here 1, 4, 7, 10. All of the values have 3 difference in between them. And as we have given our range 20, the value must end before n minus 1. So if I want to declare a certain type, for example, you can see that I'm declaring a D type here. Here is the defining a data structure type, like, mm, if I want to assign float, it would give float value. As you can see, it's like 1.0, 4.0, but it is right that just showing the decimal here. But if I just write int, it would just show us the integer value. And you can see that we can also define a string as an array. So we can also check the array type. So you can see the data type is printed here U25. So we can understand that here is a string data type of an array. Now moving to another one, how we can initialize an empty array, we can simply write the built-in function of empty, then write 3. Here is 3 is just indicating the shape of the array, so it would look like this. But uh, the values are bit different because we are not given any values initially. We didn't initialize any values, so it is looking a bit crusty, but it's like that. Now moving to the second type of arrays, like multi-dimensional, we can also declare 2D array. The complex one would be like this. So here we are taking a one dimensional array. Sorry, one direction is that. So we are passing a list, then we are reshaping with an help of a built-in function of numpy. Then we are passing the array and the new shape of the array. Then it would simply divide this list by its half. Then it is showing a 2D array. And we can also do it like this by passing a two different lists in between them, so that it can be two dimensional. And how we can figure out a shape or size simply by using the numpy's built-in function. So if I want to figure out the multi-dimensional array, here our multi-dimensional array was this. So if I wanted to know the shape of it, I will simply write multi-dimensional, the name of the variable, and then write the shape. Then it will show me the shape because I have initialized here the value of the new 2D array to be 2 comma 3. So it is showing me 2 comma 3. So we can verify that our newly modified 2D array is 2 comma 3. And moving on to figure out dimension, it is similar, but we have to write n dim, which is like the first three letters of the dimension. So we get the idea what was the dimension. As you know, we were dealing with 2D array. And lastly, to figure out the uh, size of an 2D or a 1D, we can see that size here is indicating that how many entries are here. 1 2 3 4 6. So if we slightly change, let's see what would happen if I slightly change the values. So let's say I am passing this one here. Let's check what happened. I am just changing it a little bit so that we can understand whether I'm saying right or wrong, because we have to fact check everything. We cannot blindly trust anyone, anybody. So let's keep one quantity less. So let's say um oh, it is a sitting shape one. Let's say no, it is okay. Well, let's see if I increase the value. Does it have to? Yes, it has to be same, because otherwise it won't work. It would give an error like previously. So it is okay now. There must be equal number of entries. Otherwise, that you'll face an error like me. Don't be stupid like me. So now that we have an 2D array, a bit different now, we can see that the numbers have increased. The arrays of number. Now let's see what is the shape of it. So it is saying that 2 comma 5. Actually, we can verify that there are 2 rows and 5 columns. So it is saying that I have a matrix, 2D matrix, where my number of rows is 2 and I have 5 columns here, 1 4 2 5 3 2. Now let's check what was the dimension. This is basically 2 here, but if I want to do one more dimension, then that would be like, let's do another dimension. Let's do 3D to see whether it happens or not. Let's make it 3. So we have now a three-dimensional array. So let's see. Wait a minute. Nah, yes, all of this. I'm showing you the right screen, so I'm okay now. So now that we have a 3D array, let's see. We can see that we have a three row. It is the number three is saying that I have a three row in my array and I have five columns, one, two, three, four, five. Now let's see what is the dimension here, because previously we were working with 3D one, 2D one, sorry. It is saying 2D. Why is that so? It's not. Let's see. Let's see what the AI says. If you do not understand something, just ask the AI. Three dim area. I have written the same thing. So what's wrong? Why it is not? Hmm. This. I don't know why it's happening. Why it's not showing three. Let's see. Let's learn together. Name of the variable is. Think of an attribute. In simple terms, how many does the variable? I think we cannot represent 3D arrays with NumPy. That's why we are encountering this. So it is basically two-dimensional. So that's why it cannot be three. We can only represent up to two. So we check the shape. So that is a cross verification. I don't still don't know why it happened, but I think so. We can, as far I can recall. Now let's move on to the size. Oh, 15. Now it's like 15. Now let's check 1, 2, 3, 4, 5. We have 15 entries, so we have total size is 15. So this was the introductory part and a bonus activity for today. So that is the last segment of our today's. So I am sorry once again for yesterday. I was not cautious and there was no recording of it, and I will try to give more attention, and sorry for that once again. And I hope you will come again for the the third session, where we will know more about linear algebra. I'm just touching the surfaces. So thank you for staying until now. So I would like to end the live today. I can see at this moment 18 people are seeing. I do not know who are they, but thank you for watching and seeing me uh, talk to myself or talk to you guys. And thanks for today. And that would be all. Let's see each other again.